This lesson is going to be an overview of solving systems of linear equations in two variables. You're going to find that in this lesson we treat this a little bit as a review because we assume you have seen these types of systems before. I want to point out to you that if you need additional help other than the problems that are in this particular film, there is another series of lessons on these same topics that are listed in our math lab under Chapter 7 for Weltman and Perez beginning algebra. So if you find that you need additional help, you may want to check out that other film. What we're going to do in this lesson is to review the three methods of solving a system of linear equations. We will review graphing, solving by substitution, and solving by elimination. Since we're doing three different methods of solving these systems of equations, I will separate these three types of problems with a red screen similar to the one that you saw at the beginning of this tape. That way, if you need help just on the substitution process, then you may fast forward your tape until you see the red screen that would start the beginning of that part of this lesson. Okay, we're going to start with defining what we mean by a linear equation. So let's take a look at that definition. Any equation that can be written in the form ax plus by plus c equals 0, where a, b, and c are real numbers, and with the property that not both a and b are 0 is called a linear equation. You've seen this definition before. Notice the important part again for linear equations is that your x is to the first power, your y is to the first power, the x and y are in separate terms. In other words, they're separated by a plus or a minus sign. We do not have x and y appearing in the same term together. Recall, of course, that a, b, and c are just numbers, and we want to be sure that a and b are not both zeros, otherwise we would not have any variables in this equation. But do recall that there are instances where the a might be 0, this term would be missing, and our linear equation would only contain the variable y, or vice versa. I also want to remind you what we mean by a solution to a linear equation in two variables. A solution to an equation in two variables is an ordered pair of real numbers with the property that when the x coordinate is substituted for x and the y coordinate is substituted for y, we obtain a true statement. So we're looking for ordered pair solutions x, y, where those two numbers would make the equation true. Having reviewed this definition of just a simple linear equation and what we mean by a solution to a linear equation, then we extend that idea to when we have a system of equations. That simply means that we have more than one linear equation that we have to solve at the same time. When we look for solutions to systems of equations, we're looking for those ordered pairs x, y that satisfy all of the equations in the system. And in fact, to check our solution, that's exactly what we would have to do, is to substitute that ordered pair into all of the equations and make sure that every one of those equations turned out to be a true statement. Now, we've said we can solve systems of equations where we are working with only two variables by three different methods: graphing, substitution, and elimination. I'm going to be doing the graphing method first, and that lesson will follow right after this red screen. To solve linear systems by graphing, we will follow these steps. First, we will graph both of our equations on the same coordinate system. Second, if the lines intersect, this point of intersection will be the solution to our system, and this type of a system is called an independent system. If the lines are parallel, there is no solution. This would be an inconsistent system. Finally, if the graphs are the same line, there are infinitely many solutions, and this is called a dependent system. I hope that you are familiar with this particular method and the words that we use to describe the way that the solutions turn out. As we look at these particular problems, we're going to see an example of each of these three types of systems of equations. Remember, if the lines intersect in that one single point, then the coordinates of that point would be the x and y value that would make both of our equations true. If the lines are parallel, then obviously there is no value of x and y that would be the same that would make both equations true. And then finally, if our graph turns out to be the same line, then every point on that line is a solution. We will review these names again as we look at our different examples. Solve by graphing. Our first equation is x plus 3y is equal negative 3. And our second equation is 2x minus 5y is equal 16. So the first order of business here is to graph these two equations on this same coordinate axis that I have over here. Let's take this first equation. That pen's not writing dark enough. Let me switch here and try a different one. Our first equation is x plus 3y equals negative 3. Now, one of the ways that we can graph a line is to find both the x and the y intercept. I'm going to write these as ordered pairs. I'm going to choose x to be 0. Notice in this equation, if x is 0, then this term would be 0 and it would be not necessary in our equation. So all we would have left is 3y is equal to negative 3. And of course, if we divide both sides of this equation by 3, we get y equals negative 1. So whenever x is 0 in this equation, y is negative 1. Now let's do a second ordered pair where we choose y to be 0. Of course, if y is 0, 3 times y is 0, isn't it? And so this term would not be necessary. Our equation then says what? X is equal negative 3. Since we only need 2 points to graph our line, I'm going to use the x and y intercept here. 0, negative 1, and negative 3, 0. And then remember, when we're graphing, we want to be very careful to line these points up very accurately so that we can sketch in our graph as accurately as possible. Okay, now our second equation, 2x minus 5y is equal 16. I'm going to solve this one or graph this one by a different method. Recall the slope-intercept form. Let's solve for y. If I subtract 2x from both sides of this equation, I have that negative 5y is equal negative 2x plus 16. And then we're going to divide both sides of our equation by negative 5. Negative 5 divided by negative 5 gives me a positive 1y. Negative 2 divided by negative 5 is a positive 2/5 x, notice. And then I have a positive 16 divided by 5 is going to give me a negative 16/5. So you will notice here that our y-intercept is not an exact value. We're going to have to approximate that. But remember, in this form, my slope m is 2/5, and my y-intercept given by b is negative 16/5. Recall, this means whenever x is 0, y is going to be negative 16/5. Now, negative 16/5, we know if we divide 5 into 16, it will go 3 times with a remainder of 1. So we could write this as negative 3 and 1/5, and I want to think of it that way in order to locate it on my coordinate system. So let's see, 1, 2, there's negative 3. Negative 3 and 1/5 would be just barely below that line for negative 3. Now remember, slope tells me that I will go up 2 and to the right 5. So if I go up 2, I will be just below this line and to the right 5. 1, 2, 3, 4, 5. So I've located my second point over here using slope. And now we're going to connect these 2 points. I'm trying to be very careful. keep in mind that because I had to approximate this y-intercept for this second line, I could have a little bit of a mistake if I'm not very careful with my graph. It appears, however, that my two lines are intersecting in this one point right here. Let's get the coordinates of that point. From the origin, x will be 1, 2, 3, so my x coordinate is 3, and then y will be a negative 2. Now I need to be absolutely sure that this is the solution to my equation. So what I'm going to do is to substitute this solution into both of these equations to check it. So let's just slide over here. If x is 3, this first equation will have a 3 there, plus 3 times y. If y is negative 2, 3 times negative 2 is a negative 6. And we want to know, does that equal negative 3? Well, of course, 3 subtract 6 does equal negative 3, and we do have a solution for this first equation. Now let's check in the second equation. If x is 3, 2 times 3 is 6. I have a negative 5y. If y is negative 2, a negative 5 times a negative 2 would be a positive 10. And we want to know, does this equal 16? And again, of course, 6 plus 10 does equal 16. So we can see that this ordered pair is a solution for both of our equations, and therefore it is a solution to this system of equations. Recall in our definition, if we have one single solution, this system is referred to as being an independent system. Solve by graphing 3x minus 4y equals 20 and 6x minus 8y equals negative 16. Let's take our first equation, 3x minus 4y equals 20. And I think I'm going to solve for y again here and use the slope-intercept form. So if I subtract my 3x, I have a negative 3x plus 20. Then dividing both sides by negative 4. Negative 4 divided by negative 4 gives me 1y. A negative divided by negative is positive 3/4 x. And positive 20 divided by negative 4 is negative 5. So for this equation, my slope m is 3/4. My y-intercept is given by b equals negative 5, or in other words, 0, negative 5 is my y-intercept. So let's see, from the origin, 0, 1, 2, 3, 4, 5. 0, negative 5 would be located here. My slope tells me to rise 3 and run 4, or up 3 to the right 4. 1, 2, 3, 1, 2, 3, 4. Let's connect these points. Okay. And then let's take our second equation. 6x minus 8y equals negative 16. Now let's do this one also by slope-intercept. Let's solve. So subtracting 6x from both sides. And then I will divide both sides by negative 8. I have a positive y here. A negative divided by a negative is positive. We can reduce 6 over 8, can't we? If we divide both of these by 2, we get a 3 over 4x. And then a negative divided by a negative is a positive, and 16 over 8 will reduce to 2. So for this equation, my slope is 3/4. My y-intercept is given by b equals 2, or 0, 2. So I will graph 0, 2. My slope says go up 3 to the right 4. 1, 2, 3, 1, 2, 3, 4. And then I will sketch in this second line. Do you see, of course, what is happening? These lines are parallel, aren't they? How can I know that they're parallel? Look at these slopes. Isn't it true that if two lines have the same slope, then they are parallel? Since I have parallel lines, these lines will never intersect. Therefore, I have no solution to this system of equations. There is no value of x and y that will make both equations true at the same time. If we have a system like this with no solution, this is called an inconsistent system. Solve by graphing. Negative 2x plus 3y equals negative 2, and 6x minus 9y equals 6. Well, let's see. Let's decide how we're going to do this. I think on this first equation, just to be different again, I'm going to use my x and y intercepts. So if I choose x to be 0 in this equation, this term would not be there, would it? Solving 3y equals negative 2, I would divide both sides by 3, and I would get y equals negative 2/3, wouldn't I? Okay. If we then go back and we choose y to be 0, then this term would be missing. Solving negative 2x equals negative 2, if I divide both sides by negative 2, I get x equals a positive 1. So let's locate these intercepts. 0, negative 2/3, that's going to be approximately right there. And 1, 0 is going to be right there. Let's graph this line. Okay, now let's take this second equation, 6x minus 9y equals 6. And I think I'll use slope-intercept again. Let's solve for y. Subtracting 6x, I have negative 9y equals negative 6x plus 6. And then we will divide both sides by negative 9. Of course, negative 9 divided by negative 9 is a positive 1y. I have a negative divided by a negative here, so I get a positive solution. 6 and 9 have a common factor of what? 3. Dividing by 3, I get a 2 over 3. So I have 2/3 x here. A positive divided by a negative is a negative. 6 over 9, again I have a common factor of 3. Dividing by 3, I get a 2 over 3. My slope is 2/3. My y-intercept is negative 2/3, or 0, negative 2/3. Well, notice my y-intercept is this same point that I have listed here. My slope says to go up 2 and to the right 3. So up 2 would put me just about right in there. Go to the right 3, 1, 2, 3, and guess what? I'm on the same line. If I go up 2 and to the right 3, I'm on that very same line. In fact, if you notice up here, if I were to multiply this first equation on both sides by a negative 3, what would happen? Negative 3 times negative 2 is a positive 6x. Negative 3 times a positive 3y would be a negative 9y. And negative 3 times negative 2 would give me a positive 6. So notice that this second equation is simply a multiple of the first equation. Something else you could look at, if I had chosen to solve this equation for y, notice I would have added 2x to both sides. And then when I divided by 3, I would get 2/3 x minus 2/3. Notice that equation is exactly like this one. At any rate, what we see is that every point on this line is a solution to both of our equations. The graph is the very same line. So we have infinitely many solutions. Every point on the line is a solution. If we have a system like this with infinitely many solutions, this is called a dependent system. Now, sometimes when you have a dependent system like this and you have infinitely many solutions, you write the solutions in kind of a solution set notation. My solution set S would be the set of ordered pairs x, y, such that, and remember then we can give a rule that describes the solutions. Well, what we can give as a rule is either one of these equations, because either of these equations describes the points on this line. So if I choose to use that first equation, I might say such that negative 2x plus 3y is equal to negative 2. By this we're saying any ordered pair that satisfies this equation will automatically also satisfy this equation, and therefore we have all those infinitely many solutions. Solving linear systems by substitution. To solve by substitution, we will follow these steps. First, we will solve one of the equations for one of the variables. What we'll do here is look for a variable that is going to be easy to solve for. Secondly, we will substitute the expression from this first step into the other equation. Number 3, we will solve this new equation for the one variable that remains. And then fourth, we will substitute the solution from step 3 into the equation of step 1 and solve for the second variable. And then finally, we will check the ordered pair solution in both of the original equations. So we're assuming you've done this process before, but we'll review these steps as we look at an example here. Solve by substitution. I have the system 5x plus 2y equals 9 and x plus 3y equals 4. What I'm going to do is to look at these equations and see if one of these variables might be easy to solve for. And usually what I'll look for is there a variable with a coefficient of 1? And I do see one right here in the second equation. That means it will be very easy to solve for this x in this second equation, because all I will have to do is subtract this term to get it to the other side of the equation. So let's take this second equation, x plus 3y equals 4, and we're going to solve for x by subtracting that 3y. So x will equal negative 3y plus 4. So that is our first step. We've solved one of the equations for one of the variables. Now, for the second step, we will substitute this expression that we've gotten into the other equation. Well, the other equation is 5x plus 2y equals 9. So I'm going to replace x in this second equation with this expression. I have 5 times negative 3y plus 4, and then bring down my plus 2y is equal 9. Now, we will distribute to remove our parentheses. So multiplying, I have negative 15y plus 5 times 4 is 20 plus 2y is equal 9. Notice I only have the one variable y, so I'm going to solve for y. Adding these two like terms together, negative 15y plus 2y is negative 13y. Then I have that plus 20 still is equal to 9. And then I will subtract 20 from both sides of this equation here. So let's see, that will give me a negative 13y is equal to a negative what? 19? I'm sorry, 11. Can't subtract here, can I? Negative 11. And then dividing both sides by negative 13, I get positive 1y is going to be a positive 11/13. Now, once I have this value for this one variable, I will take this value back to this expression we had up here. So, substituting for y in this expression, I have negative 3 times 11/13 plus 4. So let's solve now for x. Notice that's over 1, so I have a negative 33/13 here. And I'm going to write 4 over 1 and convert to the same denominator. So multiplying the numerator and denominator here by 13. 4 times 13 is 52. That's over 13. And then we have common denominators, so we can combine our numerator and put it over this common denominator. opposite signs here. 3 from 12 is what, 9? And 3 from 4, since I borrowed, is positive 19/13. Now that I know both of my values, I can write my ordered pair solution, 19/13 for x and 11/13 for y. Since I have only one solution, recall that this is an independent system. Solve by substitution. Do you see one of the variables in one of those equations that might be easy to solve for? Look for a coefficient of either 1 or in this case negative 1. Do you see it right here? Okay, so we're going to take that first equation, 4x minus y equals 3, and we're going to solve for y. I'm going to subtract my 4x. Notice that leaves me a negative y equals negative 4x plus 3. Now I don't want negative y, so I'm going to multiply both sides of my equation by negative 1. That gives me a positive y, positive 4x, and minus 3. Now, since I used the first equation, I will substitute this into my second equation. Let's bring that second equation down. 2y minus 8x equals 1. Substituting for my y, replacing y with 4x minus 3, minus 8x equals 1. We will distribute. I have 8x minus 6 minus 8x equals 1. Notice my two like terms here. When I add 8x and negative 8x, I get 0x, or simply 0. So on the left-hand side of my equation, I have negative 6, and on the right-hand side, I have 1. Well, this is kind of a confusing statement, isn't it? We know that negative 6 does not equal 1. This is false. If in this algebraic process of solving, we eliminate the variable completely from our equation and we have a false statement that is left, this is telling us that there is no solution to this equation. This is an inconsistency. An inconsistent statement is one that's not true. So this is referred to then as our inconsistent system. Recall in graphing, inconsistent systems with no solutions had graphs that were parallel lines. You'll find if you solve each of these equations for y, that your slopes would be the same, and those lines would be parallel. Solve by substitution. Well, in this particular one, notice my first equation is already solved for one of the variables. So I don't really have to do that step, do I? It's already taken care of. What I do need to do is take this second equation of 5y plus 15 equals 10x and replace y with this equivalent expression. So 5 times 2x minus 3 plus 15 is equal 10x. Now, if I distribute here, 5 times 2x is 10x. I have minus 15 plus 15 equals 10x. Of course, these like terms add to 0, don't they? So I have 10x equals 10x. If I get my x's all on the same side, then I have a 0 equals 0. Well, what does this mean? This statement is true, isn't it? 0 does equal 0. But what has happened? My variables have dropped out. So when this occurs, we have a dependent system. What did dependent mean? There are infinitely many solutions. Graphically, this means these are the same lines. I want to show you if we take this second equation and solve for y, if I subtract that 15, I have 5y equals 10x minus 15. Let's divide both sides by 5 and see what happens. I have y equals 5 into 10 is 2x. Negative divided by positive is a negative 3. Look at that. This is basically the same equation, isn't it? So if we did graph these, we would in fact have the same line. So remember we said we can write these solutions as a set notation. My set of solutions is the set of ordered pairs x, y, such that, and all I need to do here is list one of these equations. I think I'm going to list the first one. What we're saying, of course, is that any ordered pair that makes this equation true will also make this one true. So those would be the solutions to this system. Solving linear systems by elimination. First, notice that we want to eliminate any fractions and express each equation in the form ax plus by, that should say equals c. Eliminate any fractions. We've learned that when we have fractions in an equation, we can eliminate the fractions by multiplying both sides of the equation by the least common denominator. We want to eliminate those fractions to make the rest of the solution easier for us. And then we want to be sure we have in this kind of standard format of ax plus by equals c so we can line up our like terms. Once we've done that, we will multiply each equation by a non-zero number so that the coefficients of either x or y are opposites. Now, sometimes we don't have to multiply both equations, but this is still true because we might say if I multiply by 1, then I'm not changing a coefficient. So we will discuss that as we look at a problem or two. Then we will add the equations from step 2. What this should happen, because we have opposites in front of either x or y, is it should eliminate one of those variables. After we have added the equations, we will solve the resulting equation for the one remaining variable. Once we have the value of that variable, we will substitute the solution from this step 4 into one of the original equations and solve for the other variable. And then, of course, we can check the ordered pair solution in both of the original equations. I've been leaving that check up to you just to save a little bit of time here on the video, but that is an important step. Solve by elimination. Well, let me notice first of all that I do not have fractions in either of these original equations, and they are in the form of ax plus by is equal c. So all of that first step is taken care of. What I want to look at then is how can I get opposites in front of either the x's or the y's. Now, if I want to get opposites in front of the x's, the opposite number would have to be their common multiple, which would be 15. So I might multiply the top number by 3 and the bottom one by -5, and that would give me a positive 15 and a negative 15 in front of x. Or, if I would rather, I can get opposites in front of y. So noticing I have a -4 here and a positive 2 here, I could easily change this into a positive 4 if I multiply this second equation by 2. And then I wouldn't even have to change my first equation. So either of those methods would be correct. Either get 15 and -15 here, or get positive 4 and -4 here. I think I'm going to go for the 4's in front of the y, just because that would be one less multiplication step I'd have to do. So what I'm going to do is just simply rewrite that first equation, 5x minus 4y is equal 8. I'm going to take this second equation and I'm going to multiply both sides by positive 2. So 2 times 3x gives me 6x. 2 times 2y is a positive 4y equals 2 times 7 is 14. I now have opposites in front of y. So I'm going to add these equations together. Recall when we add, we just add like terms together. 5x plus 6x is 11x. Negative 4y plus 4y is 0y, are simply 0, so I don't need to write that down. Equals 8 plus 14 is 22. Notice this new equation I've made here contains only the variable x. 11x equals 22. I can solve for x by dividing both sides by 11. So I get 1x over here. 22 divided by 11 is 2. So I have found one of my variables. Now I am to take this solution and put it in either of these original equations, whichever one you want to put it in. So I'm going to just choose to put it in the second equation, and the reason I'm doing that is because 2 is the coefficient of y. It's a positive number and it's smaller than that negative 4. I know I'm going to be solving for y, so here I'd be dividing by a smaller number than up here. But actually it doesn't really matter. So if x is 2 in this second equation, 3 times 2 would be a 6, wouldn't it? Plus 2y is equal 7. If I subtract 6 from both sides, 7 subtract 6 is 1 there. And then dividing by 2, I have y is equal 1/2. So I have my ordered pair solution to 1/2. Now I think I'll go ahead and check this one just to show you that we do need to do this. In my first equation, 5 times x, 5 times 2 would be 10. Negative 4 times y, well, if y is 1/2, negative 4 times 1/2 is a negative 2. Does that equal 8? And of course, yes, it does. And then in our second equation, if x is 2, 3 times 2 is 6, plus 2 times 1/2, 2 times 1/2 is a plus 1. Does that equal 7? And of course, yes, it does. So my solution does check. Do you recall what we call this if there's one single solution? This is an independent system. Solve by elimination. Well, I do not have any fractions here, but notice these things are not in the correct order that we like to have them. So we're going to rearrange this. Let's take our first equation. The 3x is okay where it's located. But notice my equal sign is here. I want the y on this side, so I'm going to subtract 2y. That will move it over here as a minus 2y. And it removes it from here, so I have that positive 2 left all by itself. So 3x minus 2y equals 2 is the form I want that in. Now notice in this second equation I have 4y here. I need the x over here, so I'm going to subtract 6x. That would be a negative 6x. This 4y is understood to be a plus 4y. And that leaves the constant negative 1 on the right-hand side of my equation. So now I have everything in the correct format. Now I need to get opposites in front of either x or y. Just looking, I notice if I multiply this top equation by 2, then I'm going to get a 6x, which is opposite of negative 6. So I'm just going to bring that down here. Multiplying by 2, 2 times 3x is 6x. 2 times negative 2y is negative 4y, and 2 times 2 is 4. Be sure that you multiply all terms on both sides of the equation by this number. Now we're going to add these two equations together. Negative 6x plus 6x is 0x, or 0. Don't need to write that down. Plus 4y minus 4y is 0y, or 0. Now, I'm to my equal sign, so I am going to need to put a 0 down for this side of my equation. Over here, I have a negative 1 plus 4, which is a 3. Now, what does this mean? If our variables have been eliminated, all of them are gone. Is this true? No, this is false. If we get a false statement, this means there is no solution, or this is an inconsistent system. Solve by elimination. Well, again, there's no fractions. This first equation looks okay, doesn't it? Let's just rewrite it. 4x minus 5y equals 2. But notice this second equation is out of order again. I'll leave the 12x. I will subtract that 15y, so minus 15y. That will leave me equal 6. Now, how can I get opposites? What if I multiply this top equation by negative 3? That'll make a negative 12x, won't it? So let's multiply it. Negative 3 times 4x is a negative 12x. Negative 3 times negative 5y is positive 15y. And negative 3 times 2 is negative 6. Now I'm going to add these two equations here. 12x minus 12x is 0x. Negative 15y plus 15y is 0y. I have 0 on the left. 6 minus 6 is what? Also 0. What happens if our variables completely drop out, but what we have left is true? This is a dependent system. We have infinitely many solutions. And if we want to write the solutions in our set notation, it is the ordered pairs x, y such that, what do I do here? Remember, I just need to list one of these equations because these are the same equation. Since those numbers are smaller, I think I'll list that first equation. And what we're saying is any ordered pair that satisfies this first equation will also satisfy the second equation. Solve by elimination. No fractions, but my equation, this first one at least, is not quite right. Let's rewrite that. 7x, I'll subtract the 3y, minus 3y, and then I will have equals 9. My second equation is 2x plus 5y equals negative 4. Now, to eliminate my variables, I need to get opposite coefficients in front of either x or y. To get opposites in front of x, I would need to change these to 14 and negative 14. To get opposites in front of y, I would need a positive 15 and a negative 15. I think what I'm going to do, since these are already opposite signs, I'm going to go for the 15s in front of y. So I'm going to multiply this equation by 5, and I'm going to multiply this equation by 3. So let's multiply by 5. 5 times 7x is 35x. 5 times a negative 3y is a negative 15y. And 5 times 9 is 45. In this, we will multiply by 3. 3 times 2x is 6x. 3 times 5y is a plus 15y. And 3 times negative 4 is negative 12. Now we're going to add these two equations. 35x plus 6x is 41x. And of course you can see we're getting 0y or 0 here equals 45 minus 12 is a positive 33. Dividing both sides by 41, I have x equals 33 over 41. Now you might want to know if that will reduce. Well, we know the only things that divide 33 are what? 3 and 11. Will 3 divide evenly into 41? No. What about 11? Will it divide 41? Again, no. And so we cannot reduce this fraction. Now, in our steps, it was recommended then that we take this solution and substitute it into one of our remaining equations to solve for the second variable. And we can certainly do that. But I want you to notice with this fraction, if we substitute this fraction in up here and solve for y, we're going to have a lot of work dealing with fractions, aren't we? So I'm going to suggest that we do an alternate method here rather than substituting 33 over 41 into one of these equations. Let's go back to these two equations as we had them written here. And notice that here we eliminated y. Well, let's go back and eliminate x and see what happens over here. So to eliminate x, I will multiply this top equation by 2. 2 times 7x is 14x. Negative 6y multiplied by 2. 9 times 2 is 18. Since I made that be 14x, what do I want to multiply by here? I want it to be a negative 7, so I'll get a negative 14x. Negative 7 times 2x is negative 14x. Negative 7 times positive 5 is negative 35y. And negative 7 times negative 4 is a positive 28. Now let's add. 14x minus 14x is 0x, or 0. Negative 6y minus 35y is a negative 41y. And adding 8 and 8 is 16. I'm carrying 1, so that's a 46 there. We will divide both sides by negative 41. That gives me positive y. I'll have a negative 46 over 41. And again, you might be asking, can I reduce? Well, you know that 2 will divide 46, but 2 will not divide 41. If I divide 46 by 2, the other factor would be 23. 23 does not divide 41. So neither of these fractions will reduce. My x-coordinate is 33 over 41. My y-coordinate is negative 46 over 41. And of course, this is an independent system because we had only that one solution. This is a good process to use here when you do have these kind of horrible looking fractions as solutions. Instead of taking a hard fraction and substituting and having to work all this with fractions, you can simply go back and eliminate the other variable that you did not eliminate here. Now, of course, we need to be sure that these two numbers satisfy both of our equations, and we could do that by checking. I'm going to leave that check up to you, and you'll find that this is indeed the correct solution. I have one additional problem that I'd like to work for you. Notice this one has fractions in it, doesn't it? 1/2 x minus 1/9 y is equal 0, and 1/5 x minus 1/4 y is equal 3/20. Now recall our first step suggested that we eliminate our fractions. In this first equation, my common denominator is what? 2 times 9 is 18. I'm going to multiply by 18. Now 1/2 times 18 is what? 9x. Notice you've got a minus sign here. 1/9 times 18, that 9 would cancel in 18, leave a 2, wouldn't it? So minus 2y. And 0 times 18 is still 0. That equation looks a lot better, doesn't it? What is your common denominator here? It's 20. So we're going to multiply by 20. 1/5 times 20. 5 cancels into 20 and leaves a 4, doesn't it? So I have a 4x. I have a minus sign. 4 cancels into 20 and leaves a 5 times 1, so minus 5y. And the 20s would cancel when I multiply, leaving me 3. Okay, so I have a new system here. This is just an equivalent system. We're going to look for opposites in front of either x or y. I think what I'm going to do is, since they'll be smaller numbers, let's get these to be 10 or negative 10. So I'm going to multiply this equation up here by 5. Let's see, 5 times 9, I have a 45x. 5 times 2 is 10, so minus 10y. 5 times 0 is 0. Since this is a negative 10, I need this one to be a positive 10, so don't I need to multiply by negative 2? Negative 2 times 4x is a negative 8x. A negative times a negative here is a positive 10y. And negative 2 times 3 is negative 6. Now let's add here. 45x minus 8x is 37x. Minus 10y plus 10y is 0y, or 0, equals negative 6. Adding here. Dividing both sides by 37, x is negative 6 37ths. Now, again, we have a choice. We can take this solution and substitute it back into one of these original equations, but that looks kind of hard, doesn't it? Or, what else could we do? We could go back here and eliminate the x instead of the y. Let's try that. If I eliminate x, I need to have either 36 or negative 36. So let's go back to this, and we're going to multiply this top equation by 4. 4 times 9x is 36x. 4 times negative 2y is negative 8y. And 4 times 0 is 0. Then I want this one to be negative 36, so we will multiply by negative 9. Negative 9 times 4x is negative 36x. A negative times a negative is a positive. 5 times 9 is 45y. And negative 9 times 3 is negative 27. Notice when we add, our x's are eliminated, 0x. Negative 8y plus 45y is 37y. And I have a negative 27 when I add over here. And then finally, dividing by 37, y is negative 27 over 37. This fraction here will not reduce. My solution is negative 6/37 and negative 27/37. And of course, this is what? Independent, isn't it? I hope these examples has helped you to review your methods of solving a system of linear equations when you have two equations and two variables. Graphing, graph on the same line and look for points of intersection. Substitution, you look for a variable that is easy to solve for in one of your original equations, solve for that variable and use that to substitute in the other equation. And then elimination, where we try to get opposites in front of either our x or our y. You'll find that the techniques you've learned here are going to be very helpful when you get larger systems of equations that you need to solve. This completes this particular lesson. I would appreciate it if you would rewind this tape before you take it back to the math lab. Thank you very much.